Ciao! Here is a conversation with Daniel Pérez Palau. Dr. Palau is a professor at the Universidad Internacional de La Rioja. He completed his PhD in mathematics in the Dynamical Systems group at the University of Barcelona. After that, he joined the French Space Agency as a postdoctoral researcher working on optimization problems. Now, together with teaching, he's focusing on new research areas, such as artificial intelligence. I hope you enjoy it. To support this project, please subscribe to my YouTube channel, connect with me on Twitter and LinkedIn, and support me on Patreon with a monthly membership, following the links in the description. For me as well, the main point of these conversations is to fill the gap that COVID left.
It's a very nice initiative and a very nice thing that you fill this gap and try to at least to join people while we don't have conferences and so on.
Yeah, I feel like I'm looking for. It's also there's the advantage that I can choose the people to which to talk to, and in that sense, it's easier. I'm not constrained by the conference. The people that are attending the conference. But at the same time, it's not in person, so there's something missing.
Yeah. What I always miss is the coffee. For me, it's not the same to have the coffee between us and just some cookies or something like that. Then it has something that it smooths quite a lot the conversation and so on.
Yeah. Okay. You're talking to someone that never attended a conference.
Okay.
Because this is my first. I just finished my first year as a PhD.
Okay.
So COVID started as soon as I started doing research.
Okay. So
So
you have never experienced it, what a coffee break is, and
yeah, I can imagine it. I attended some workshop,
okay.
But yeah, I can see what's missing. And actually, I started recording these conversations before the pandemic because I already felt the urge to bring together scientists in some way, to make use of the internet in some new way, to let's say to make conferences virtual. And I could see also looking around now during the pandemic that a lot of groups are now moving to the internet for these kinds of meetings and presentations and also
even
conferences themselves.
Even PhD dissertations, that is something nice that sometime before the pandemic I couldn't attend to the dissertations because they were like half an hour by train plus the time of the dissertation and so on. And now, since they are public and they are doing them through internet, I can attend most of them because you have the link, you just connect, and so you there are things that are much better now than before. But of course, we have this personal link that is losing. But well, we have to stay with the good things and try to don't think about the bad ones.
Yeah, maybe we can start by discussing about how we are coping with the pandemic and how your research influenced by that. If you can share that.
Oh yes, well. I work in a university that works always in through the internet and in distance. So we don't have neither offices, neither physical classes. So everything is through internet. So you can see my office that it's always my office at home. And from that point of view, the pandemic doesn't affect me a lot in terms of moving around and so on. But our students were much more active than before. Just they had a lot of time. So since they have a lot of time, we don't have they work much more than before, and we need more time just to attend them to solve their problems and so on. So since the amount of time is limited, there were more time dedicated to attend the students and less time to do research. So I think that it's something that for me, it went in the reverse way that a lot of people that they don't have classes to do, so they had much more time for doing research. And for me, it had been the other way around. So I am struggling a little bit to feel time to do research. But well, from time to time, I try at least spend one day doing research every week, and that's quite a lot now. So
And what are you working on now in your research?
I am so I started doing research in astrodynamics and so on. Then I moved to CNES and I continued doing things about spacecraft and optimization of trajectories and so on. And now I end up in a group that it's a group that they have a lot of computer scientists and a lot of people working in artificial intelligence and machine learning and things like that, and also this image recognition and so on. So what I am trying to learn their techniques to apply them back to the astrodynamics and celestial mechanics things and so on. So I hope that at some time we can do some kind of optimization things and visual processing and image processing just to apply to the things that they have been done just till now with their expertise and so on, to mix all and wrap everything to mix all of both worlds that are quite interesting. So I'm in a phase of my career that I am still working a little bit in the celestial mechanics, but I am also learning new things, and almost it's like starting again from the beginning, just to say, okay, what I can take from the from the AI thing to bring to my world and to improve my world. So I am in a stop and like thinking time to improve a little bit what I am doing through using other kind of techniques and so on.
Okay, like what do you already have a vision of which techniques to use coming from AI to be applied in celestial mechanics, or you're still looking around the AI
Well,
field?
I am looking around and I am working in collaboration with just working in what they are working, just to see if it's interesting or not to bring to my topic. For instance, one thing that I think that it can be used for sure, it's in one of my works at CNES. We worked about optimization orbits using these indirect methods, and at the end of the day we did like a massive explorations, and we found a lot of optimal trajectories just to travel from the earth to the moon using low thrust. And we did a lot of work just analyzing trajectory by trajectory, which how they look and which kind of devices, like which invariant manifolds they were using and so on, just to say, okay, this is the structure, and we can do some kind of families of orbits that they are that each of these optimal trajectories are following. So using these techniques of machine learning and automatic uh, grouping and so on, just to that this kind that it was quite hard, and it took us a lot of time because it was just looking orbit by orbit. It can be done automatically by the computer and so on. So I think that this will be one of the things that can be done. And the second thing that I hope that, and this is a very big hope, and I am not so sure, is about the use of this artificial so the AI, but just to optimize things and let the optimizer be like a neural network or something like that that automatically determines which is the magnitude of the thrust that you have to use or something like that. I hope that this can work also, although it's not quite straightforward. So I am trying to convince some specialists on this topic just to bring them to celestial mechanics and to try to use their expertise to improve the optimization that we are using. So these are the two things that I am working on this more like in the AI. And then from the point of view of image processing, that we have also several, there are several colleagues in the group that they are working on that. We started a completely different topic that is to analyze the atheroma. I don't know if you know what's that. It's
No?
in the veins and the arteries of our body. So from time to time, there is some small amounts of calcium or what, I don't know exactly what's the medical explanation, but the idea is just to analyze the tubes of the arteries and the veins and to detect things there that some kind of special formations that appears. So the idea of that is that these techniques can be applied also what I did at the very starting of my career with the Lagrangian coordinate structures. So just to use this automatic detection of structures to complement the Lagrangian coordinate structures and all these kind of things. So I am like revisiting several things just from a new perspective and from a new point of view that for sure not all of them will work, but I hope that some of them will go on.
Mm-hmm. So you're really researching now. You're really looking around for ways to match the new field in which you're entering and
Yeah,
everything you know, everything you went through during your PhD and postdoc.
yeah, yeah. So I'm not producing a lot, that's for sure, but I am touching a lot of things and trying to learn a lot of things just to see which can be the new ways to proceed and just to innovate a little bit and to
Mm-hmm.
think a little bit out of the box on
Yeah.
how
Yeah, if I
can.
can add something, I saw some works, recent works produced to perform optimal control using neural networks. So I think that that's already a rich field. I mean, it's a valuable road to go,
Yeah,
and yeah, but also the other ideas. I mean, they're as interesting as, if not more, particularly the automatic detection of Lagrangian coherent structures. I found it really fascinating, and I think there's some value there. Um, and maybe we can now go back to the origin of this conversation, let's say. So I called you. We had a first contact because I was studying your works
yeah,
for a journal paper I'm working on, and your works from your PhD, and in particular the ones combining the jet transport technique with Lagrangian coherent structures applied to celestial mechanics. So could you maybe expand on the work you've done during your PhD?
yeah, sure. So I started, maybe it starts with my master thesis that I started to work with the Lagrangian coordinate structures and just to look around what they were doing, what kind of information can it give to us. And the main point was, okay, I have the invariant manifolds and there is something that I can compute and it's very nice. For instance, in the restricted three-body problem, I can compute periodic orbits and can compute the invariant manifolds, and the invariant manifolds give me a lot of information of how I can move around the restricted three-body problem. But what happens if I have some perturbation that it's not, that I cannot understand, or that I cannot put in formulas like it can be the solar radiation pressure or something like that, that give you some perturbation that even it's not periodic. If it's periodic, maybe you can compute something similar to an invariant manifold, or you can expand and to change from a periodic orbit to something that is quasi-periodic, and you can compute also some kind of tori or something like that, and you will have also the invariant manifolds. But what happens if it's not um, something periodic, or for instance, the solar radiation pressure, you can have it, and it depends on the sun, and it has some periods, but it's not as regular. And so, what can we do to understand the problem with that point? And it was when my advisor told me, okay, maybe you can use these Lagrangian coordinate structures to try to understand what they are doing, and a little bit. It was my first contact with them. So I spent maybe 1 year just doing computations and doing to learning how to work with them and so on. And the idea of the Lagrangian coordinate structure is quite simple. It's what we do is we look what happens to two trajectories that are quite close, to initial conditions that are close, and we look if they are at some time, after some time, they keep close or they are quite far away. And we give a value that it's more or less the distance that they are at which they are once we spend, for instance, 1 unit of time or 10 units of time, or fixed units time. So the idea is that we look which are the highest values, and we say if there is a high value of this distance, it means that something happens in between. That was the history behind the Lagrangian coordinate structures. So it seems that it has some relation with the invariant manifolds, because invariant manifolds also separates regions. So if you have something that it's at two different sites, you will have something that will be after some time a very, very long distance from one to the other. So we started working with that, and at some point of your computation, you need to compute the variational equations and the certainty matrix to compute this distance. That it's not exactly the distance, but we can think to understand, and in a naive way, we can think that it's a distance. Mm-hmm. So since you need these variational equations, we say, okay, we know a technique that allows us to compute these variational equations, but not only the variational equations, but also the higher order terms of the variational equations. And let's try to use it to see if we can improve a little bit this technique of the Lagrangian coordinate structures using more information that we have only with the variational equations. And it was when we started working with the jet transport, or if you talk with people in Milano, they call the differential algebra, that it's exactly the same. So we give different names,
so it's
but
a Taylor,
yeah,
Taylor polynomial expansion of the state of the system.
Yeah, the Taylor polynomial, it's an infinite series, so you never end. And in the traditional mathematics, the jet is called just the truncation of the Taylor polynomial through up to a certain order. So this is why in Barcelona group, that is where I came, there were these jet transport, that we are transporting the truncation of the jet through the differential equation. It was this was the origin of the word, of the name. And the differential algebra, it's because you are doing algebras with the differential, so with the differential part of the equation. So most of them has sense, and for me it's fine one or the other. It's just a matter of what we use usually, and it's fine. So at the end of the day, we use this jet transport, and just we started using only to compute the finite Lyapunov exponents that you need to compute the Lagrangian coordinate structures. But we say, okay, since we have more information here, can we use and can we extract and expand and try to use other kind of distances, or a more fine distances, to see if maybe the order 2 affects in some way to this distance, and or the order 3 or 4 or whatever. And can we use this other information that we have to put it in this computation of the distance? And this was the one of the reasons that we mixed both kind of things, then we move away from the Lagrangian coordinate structure that it was our main comparison point, and we try to develop different indicators and different things that can say something similar to this Lagrangian coordinate structure, that is how behave the state of the system on time. So it will behave in a similar way to orbits that are close by, or will behave in a very different way. And this was one of the main things that drive through my thesis. So we developed all the jet transport things. We developed different techniques. We developed propagators and so on. And then we applied to the Lagrangian coordinate structures, to these new indicators, and so on. And once we had all this machine, because it's a big machine that we developed for a long time, we say, okay, but maybe we can address other problems, other things, other kind of problems that can we address with this technique. And we started to think that since what we were doing was propagating like balls of uncertainties, or balls of initial conditions, we maybe can apply that to study collision problems, or collision of two satellites, or collision of a satellite with a cloud of debris or something like that, that it's traveling around the Earth or the space. And we developed like a second part that at some point we stopped because we didn't have time enough to complete. And it's quite, I would like to return back to that topic and to work a little bit more on, because there are some things that are not finished yet, but well, it's like, the state is what it is, but we start working in this how to propagate uncertainties, and how to study the uncertainty of a spacecraft, and how to say, okay, if today I have the spacecraft that maybe has a Gaussian distribution, but I don't know where it is exactly, how can I use this information just to propagate and to say where it will be after some time, maybe tomorrow or next week. So it was an idea that we were developing, and I know that there was a Chinese guy, I don't remember now the name of him, but it was working in orbit determination using the jet transport also. So, and using this kind of techniques, it did a very good work also. So it worked here in Barcelona for a year, but I don't remember the name. So I can maybe check at some point and send you if you are interested in this kind of.
Yeah, for sure. I mean, my group is focused a lot on propagation of uncertainty. My position in particular, I'm working on uncertainty quantification and propagation. And people in my group developed what's called the generalized algebra. So it's spawning from, I think spawning from differential algebra, or developed independently, not sure. But the idea is to use different polynomial bases, so Chebyshev polynomials, for example, and do the same trick, so to propagate sets instead of initial conditions under some flow, under some dynamical system. So for sure, that's interesting. Yeah, that would be interesting if you could send me that. So chronologically, you first applied it to Lagrangian coordinate structures and then to uncertainty quantification.
Yes, the chronology was that because it was a technique that Professor Simon gave us in a master subject, and he said, "Oh, there is this," but he explained it as like a known thing, and then I learned that it was something that was quite innovative, and that there were not a lot of people working on that. So when I did the subject, it was like, okay, there is this technique, like maybe like Runge-Kutta, that it's not something that it's quite known, and everybody knows and so on. So for me was at the beginning was like that, and then I learned just talking with other people and so on that it was not so common to use this technique. So it was when we decided, okay, let's try to use it to apply to different things, and we started with the LCS, and then we moved to the uncertainty quantification.
Yeah, something I'd like to discuss is the nomenclature and also the history of Lagrangian coherent structures. So when you presented them, you said that there's some kind of distance associated to initial conditions that are really close together. And there's a lot of work, which I think it's older, and it's also independent. So I'm not sure. I think it's the same thing as the jet transport and differential algebra nomenclature. They've been developed independently from different groups, different fields of research. But yeah, there's a lot of work done, for example, by mathematicians, but also engineers working on asteroid motion to detect chaos, so the development of chaos indicators. So there's a bunch of names for you mentioned finite time Lyapunov exponent. There's the fast Lyapunov indicator. There's the Lyapunov characteristic exponent. A lot of names that indicate the same idea. So I don't know if you ever encountered this tricky aspect of dealing with the same idea but reading different names.
Yes, and a lot of times because so in our world, well, I did my mathematician. So I grew up as mathematician. So I study math and so on. And from a point of view of math, it's all very pure. And some of mathematicians likes to say, no, math is nice because it's math, and we don't need any application of math. I didn't match quite a lot in that feeling, and I looked for some place where to apply what I have learned. So is why I started to work in this more engineering world. So uh, at this moment, I am in a point that I am too applied to be mathematician, but too abstract to be engineer. So I am in the middle of nowhere. Like the good point is that there is a bunch of people that it's like me, so I am not alone. But I learned that from time to time there are some names and some things that when I as a mathematician know with a name, and an engineer know as another name, and maybe a physicist know that thing as another name. It happens with the state transition matrix, or it happens. So there are a lot of things that has different names that at the end of the day are more or less the same. So it's something that I learned just to when I don't know something or something someone asks me about a topic or for instance what you were saying, the Lyapunov exponent or the finite time Lyapunov exponent, or which are the difference. It's okay. Let's a little bit, see which are the differences. Let's compare a little bit between them, and most of the times, at the end, it's the same. There are small differences, but the idea that that it's behind, it's more or less the same. So it's true that, for instance, as mathematicians, uh, well, I will say they or we, I don't know which word to use, uh, but mathematicians don't like the finite time. So because finite time, it's something that it's like, it's not a characteristic of, it's not a general characteristic, but something that will happen in a small time. So we use the Lyapunov exponent or the Lyapunov characteristic or something like that. That it's a limit when the time goes to infinity of more or less the finite time Lyapunov exponent. Let's say there are small differences, but more or less is that. But from a point of view of an engineer, uh, it's more interesting maybe the finite time, because you don't mind what will happen when the universe will end, because it's too far away. We need something that it's closer to to what we are doing now. Or for instance, it's something that happened to me visiting Professor Howell in the States, that I was focused and I was trying to do some regularization in the restricted theory problem because I wanted to avoid the collision with the moon, with some orbits that happen to me that give me bad results with the Lagrangian coordinate structures. And she told me, okay, but why you want to compute this regularization? Oh, because maybe I am too close to the moon, and if I am close to the moon, the Lagrangian coordinate structure will give me bad results and so on. And then she told me, but if you are doing the regularization, you are already inside the moon. So you already crashed the moon, so you don't need to compute the regularization for those cases because these are cases that will never happen.
Right.
So it's the two ways of thinking and the two ways of how to look at the same problem that I learn a little bit to mix them, and I like to say that I am not a mathematician that works with engineers, but we are the same group of people that we are working the same problem, and there are different points of view, of course, but both points of view are interesting and have their own interest and their own way to progress and to make the problem advance and to find solutions about that. So I think that I have gone a lot of of your question, but I don't know.
No, you were answering, and also I can add maybe something that I have the feeling that we will have to do, and we are both doing it actually. So it's a feeling that's based on some facts. That also computer science is going to become a strong component of every expert in our field. In the field of celestial mechanics, let's call it astrodynamics, whatever. But the distinction between computer scientists and space engineers and applied mathematician is shrinking, I think. And I mean, we are two examples, but as you said, there are many people that don't really fit in one box, and so it's something interesting to see, and also it's a nice place to be. I think you can confirm this or not, to look for really new ways of doing research, new roads to look into, because you have a lot of cross fertilization just by being yourself.
Yes, actually, we already talked about the AI and so on, that it's emerging quite a lot in the literature and so on, and for sure so. I don't like people that just focus in one thing, and so you must be open to other ideas and to other things that for sure will improve and will enrich the research that we are doing.
Mm. So I have one question about related to your PhD still. I mean, not directly, but one idea I had looking at your body of works is so you applied the jet transport to Lagrangian coherent structures, then you applied it for uncertainty quantification. Then you looked, as you said, in the relation between Lagrangian coherent structures and invariant manifolds. Not in this order, but these were the main points, let's say. Did you ever think about putting together in some way Lagrangian coherent structures and uncertainty quantification? So using LCS for computing the probability of collision. I don't know.
No, we didn't. It would be probably something interesting to do, but the way of the LCS, we end up saying, okay, it's something quite equivalent, but we didn't like. And at that time, I was in a mathematician mode, in the sense that, okay, I had the invariant manifold, and so I can try. If this is invariant manifold, that was the LCS. So they were not matching completely 100%. And since I was in this mathematician mode, and I say, okay, this is not interesting because it will not go well with what I am doing.
Mm-hmm.
And we stopped a little bit this LCS thing. Later on, I revisited the topic and I say, okay, let's look again, and so on. And we'll start to look that there is also information that we can extract from the LCS. And this was the ideas that we start to move again, and it's why I'm trying to learn new things to apply them to the to try to detect them automatically and so on. And yes, we observed that for stability, practical stability reasons and things like that can be used. I don't see a direct way to use with to compute the probability of collisions or something like that, but maybe thinking a little bit, it could be interesting also.
Yeah, it's an open. I don't have an answer. I just
Uh,
said just looking at your topics, let's say the keywords of your research, and also inspired by a work which I found interesting by Ross, the astrodynamicist, um, which worked a lot recently on Lagrange coherent structures, and
yeah.
recently published a work on how to perform reduced order modeling using LCS for some kind of fluid in the flow, I guess, some continuous flow. So I was thinking, okay, LCS can be used even for reduced order modeling. That's nice. I haven't looked the paper. I just read the abstract, but I thought, okay, maybe there's something we are still not leveraging from LCS that could be used for uncertainty quantification. That was just my.
It-
I don't know if you
yeah.
have something to add to that.
It's interesting. I never thought about that because, as I said, it was like for us it was two topics very different and very isolated. So the marriage point was the jet transport, and from the jet transport we say, okay, applications that we can use with the jet transport or that and that. But it's true that we never did like it's a triangle. We never
Yeah.
joined the remaining edge. So it would be interesting to think a little bit and try to close the triangle.
Yeah. Can we now go into your work you did during your postdoc and in the details of the technicalities of the optimal control? You mentioned that you worked on low energy transfers from the Earth to the Moon.
Yeah.
Uh, which kind of techniques did you apply to do that?
So when I started the postdoc, I was in the CNES and working with Richard Benoit, that he's a specialist in what is called indirect optimization. That the idea of the indirect optimization is to use the Poincaré maximum principle to find the optimal solution of a problem. So the idea is that you have to solve a problem, let's say to minimize the time or to minimize the fuel, given an initial conditions, a given vector field that in our case was the resistive body problem or the bicircular problem. So we started with that in mind, and with this kind of indirect method, so with a direct method, usually what you do is you say, okay, I am in point A, I want to arrive to point B, and I will discretize around all the trajectory, and let's say, each day I will put a cutting point, and I will try to arrive from A to A1 to A2 to A3 till I arrive to B, that it's my final solution. And what you do is you have a bunch of intermediate points. And since you are cutting the problem, it's easier to say from point A to point B, I will arrive using that orbit and using that thrust and so on. So this is the direct and usual way of working. and probably the way that it's more used, let's say. With the indirect optimization, what you do, you look, instead of putting more points, what you do is you introduce a bunch of variables that are called co-states. So you have your states and your co-states. And with that bunch of variables, you introduce some additional restrictions to your problem. So instead of working in a problem that it's, let's say, 7-dimensional, if you are taking into account positions, velocities, and mass of your spacecraft, you have 14. So for each state, you have a co-state associated. Then the idea is that you can, if you fulfill some conditions, so you increase your initial conditions or your final conditions, the restrictions on those conditions, you restrict a little bit more. So you can guarantee that you are in an optimal solution. So the idea is that you put more initial conditions, more variables to integrate, but you guarantee that you are in, if you find a solution of that, you will guarantee that that's an optimal solution. So this is a little bit different. Instead of trying and doing this kind of shooting methods to arrive to the solution, you try to find a solution of that problem that it's bigger in some sense, but has less intermediate points.
Okay.
So the idea was to use that, to incorporate the low thrust and to go from the Earth to the Moon in an optimal trajectory in terms of fuel, not in terms of time. That because, well, for the nature of the low thrust devices, you cannot expect to have an optimal on time, but an optimal on thrust, on fuel. And the idea was that, and we started to try and do things, and what you end up doing is just a shutting method to find this solution, because you have a boundary problem that you have the initial condition, you want to arrive to a final condition, so you try to solve that. The problem was that this problem was quite difficult to solve, because since you are using low thrust, you cannot do a large thrust and to break down your spacecraft. So you cannot do this kind of arrive to the moon, like I arrive tangency to the orbit that I want, and I break down and I stopped in that orbit. But you need to do kind of spirals, spiraling down to the moon to decrease your semi-major axis, essentially. So we had problems, and we tried first continuation technique, just starting very far away from the moon, from the orbit that we wanted, and start decreasing the orbit step by step with a continuation. So each time the duration of the flight was longer, but we arrived to a shorter distance, closer to the moon. But that didn't work. So we say, okay, let's try to do some massive explorations just to see if we can find some kind of results, and doing some tricks. Instead of working from the Earth to the moon, we did backwards propagation, because in the problem assumption we had a propulsion in a high thrust propulsion in the exit of the Earth, just because the launcher can give it. So this helps you to say, okay, if you arrive to that orbit or to that point with a different velocity, you can break down using your propulsion, your high thrust propulsion. So we did this change of idea to work in backwards propagation, just to take profit of this kind of trajectories. And we did a bunch. So I remember it was a summer that I spent the full summer just exploring initial states, final states, just to find a bunch of trajectories that we end up by classifying in different families of orbits that we like, and we say, okay, there are these four main families of orbits that they are like very long time but very short fuel consumption. They are medium time, medium fuel consumption, so on. So we did this kind of classification. So this was the main work that we did. And once we finish that, we say, okay, now let's try to expand that and to move to what happens in a real system. So we were working in the bicircular problem, but the bicircular problem has some difference. I was in a PhD defense. I think that was last month or in December. I think that it was that they did some experiments, and for instance, the L2 point in the bicircular problem doesn't behave as in the restricted problem. So there are interesting things there that you cannot say that it's exactly the same. So we say, okay, we want to apply for this phase in the moon when we are close to the moon. Let's try to see if we can do some kind of optimization also here to find the orbit that we want. So we started in a quite far orbit, and the objective was to reduce the semi-major axis and to arrive with a given inclination to the orbit that we wanted. So the idea here was, okay, let's start by what I would do if I was driving. That is, I want to go there. So I will point there just to see if I can arrive. And this more or less worked, but we observed that we cannot ensure the optimality of the trajectory. So to ensure that, we say, okay, I will go there, but I will put on my thrust a coefficient that will allow me to ensure the optimality by using the Lyapunov functions.
Okay.
That the idea is, if I have a function that the derivative, so if I have a function that is that give me the function of the objective function, and I can compute derivative on them. If I am negative, I will decrease, so I will optimize. This is the idea of this Lyapunov function theory, that you have something that is equivalent to your objective function, and you look for negative derivative of your movement. And using this coefficient that we added at the beginning, we managed to see that for some orbits, this function was always decreasing because it has negative derivative. So we were going to an optimal point. So this is the idea of the second part. And the advantage of that was that we were working in a full ephemeride problem with perturbations and so on. So honestly, I don't remember now if we put a lot of perturbations or not, because the idea was to put them. And at some point we were discussing which perturbations do we put. And I remember that we added for sure Earth and Sun perturbations because we were around the moon. And I don't remember now if we added the perturbation of solar radiation pressure or something like that. But in principle, should be relatively easy to add to the program. It's just to compute this function with these perturbations, and it was prepared. But since I moved, so I finished my postdoc, I started working at the unit where I am working now, and it was quite messy days. And as I told you, I started working in different topics, and the group where we don't have a celestial mechanics group in my university now. So I was quite completely alone in that part. I keep collaborating with people that I was working, but I didn't have a lot of time to work on them. So it's something that it's there waiting for me to have time to come back and to finish some of those things that for sure are very interesting, but unfortunately the time is finite, and we well, I would like to work, but I have a lot of students to attend and so on. So I try what I can.
Okay, and how can you tell me a bit about the teaching to close up the conversation? How is it going? Let's say, how is the experience of teaching going for you?
I love teaching. So the point is that actually when I finished my PhD, my postdoc at NES, I was thinking, okay, maybe I go to a secondary school to teach, just because I like to teach. So I was thinking, okay, I will prepare the courses that I need just to be accredited and to that the state allowed me to go to. So I don't know exactly each country works a little bit different, but here in Spain you need to pass some master courses to allow to be able to go to secondary school, and just to teach math and to teach some maybe physics or something like that. I would like, but I had that opportunity in the university where I am now. That it was like a surprise for me because I was not expecting to find a job at the university, and it was quite fast. So I was one day in a conference and I received a call. Look, I have seen your CV. Do you want to come with us? Because we need a professor for mathematical modeling. And I say, okay. And from that time, I started to look a little bit, and the job was interesting. And I really like to teach a lot. And if you ask me, what do you prefer, research or teaching? Probably I will stay with the teaching. And the problem is that I think that you cannot teach at the university without research.
Mm-hmm.
So you need both of them. And and at some so what I like more is just to see the students, how they progress, how they start knowing nothing, and how step by step they progress, they advance, they do interesting questions and things that the students themselves say, okay, uh, I didn't understand that, but now I understand and I have that question. And so these kind of things that you see that you have put a seed in them and it's growing, and now they have some questions that they would never have and they would never think that they will have. And these kind of things is what I like of the teaching
Nice.
and all that. It's true that I miss to be in a classroom just teaching with the students with me, because everything that I do is with a webcam and so on. So I miss this of looking at them and their faces, and if they are like that, that you see you are not understanding anything. Okay, I will recap. Or if they are with a smile, and when do you do some jokes, and that it's not the same. You feel this feeling, it's missing still. But I think that at some moment we will be able to fill the gap with the internet also. And
Okay. You think
yeah,
so? You think we can?
sure, sure. Nowadays, I would never think that I would have more than half of my class studying from America, for instance. And now I have half of my class from America for sure. So at some point, I think that this can be closed for sure. It's a matter of time and maybe technology, but at some point we will be able to feel closer. And maybe I am not saying like in Star Trek or Star Wars that they have all these fancy things that the professor is just like how it's called, these images that are in
The
3D,
hologram.
in an hologram, but something more closer that you can see the students and you can. I think that it will be possible.
Yeah.
I am optimistic in that
I mean,
sense.
for sure, COVID is putting a lot of pressure in that sense.
Yeah.
Also, the software we're using now, for example, I mean, they're growing a lot. They're changing quickly to adapt to the situation. And I was thinking you were about to say, I hope we can soon go back to in person. But you said, I hope we can soon fill the gap with the technology. And I mean, yeah, I don't see why not.
I mean, for sure, in person will be always different. It's, for instance, not the same to do some game board, table board games. For instance, to play Risk or Monopoly or those big games, or maybe Catan or those that are newer, with friends that through internet. It's not the same. So the experience is, you have the beer, you have the whatever, the jokes, the things that happens around the game are not the same. But nowadays you can do it, and you can meet people, you can meet family. So I think that it's closing quite a lot, and there are steps still to do. But at some point, I think that it will be possible. That doesn't mean that I don't like to meet people in person. So if there are conference again, I would like to meet you in a conference and to take a coffee. That for sure. But meanwhile, and to feel a little bit these times. So, for instance, maybe we don't need to go to a conference just to talk, because we can just talk through whatever software that we are using, and that's fine. And we don't need to to wait for the conference that will happen in September. And is this so the mixture and the fusion of both? It's like we were saying before. It's not I am mathematician, and so I am scientist, and we work in different things. And so I think that it here happens the same.
Yeah, 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 for sure. I can see it after the pandemic, as an example, a small example. But after the pandemic, I'm gonna continue this project. So because it's useful, it's I mean, it's, as you said, we don't need to wait 6 months. We don't need to go the other part of the world to have a coffee and discuss, but we can discuss about technicalities and also just meet each other virtually. And that's something we can take from the pandemic. We can learn. We can, yeah. So, yeah, thanks a lot for your time.
You're welcome. It has
I
been
really
very nice
appreciated the conversation.
it has been very nice to be with you, and to break down a little bit the students, and to talk and to do some retrospective of my job. That it has been a long time that there were some topics that I had never I didn't revisit it. So it has been very nice to explain you. And as I told you, if you whenever you need some help or some advice or whatever, just ask me, because I am open. I am either by mail or through any other social media or social network. I am open to talk and to collaborate.
Yeah, thanks. That's a really nice way of working to see.
Sure.